Welcome to this concise tutorial on Probabilistic Graphical Models, or PGMs. This course follows the paper Probabilistic Graphical Models, a concise tutorial, which is freely available on arXiv. In this first lesson, we will work through sections 1.1 and 1.2. We will provide a brief overview of a framework for reasoning under uncertainty, and then provide the three main tasks in the subject, which is representing a model, performing inference, and learning from data. I will assume that you have seen basic probability notation, such as random variables, conditional probability, and sums or integrals, as well as some introductory linear algebra. We will develop the graphical model ideas as we need them, so you do not need prior experience with Bayesian networks or Markov networks. My name is David. I am a PhD student at Stellenbosch University, and my work involves probabilistic graphical models. I also care a great deal about teaching, so this series is my attempt to explain these ideas clearly while challenging myself to build useful lessons for YouTube. Let's begin with the two subjects that PGMs bring together. Probabilistic graphical models combine probability theory with graph theory. Probability provides the rules for working with uncertainty. On the left, the joint distribution over 5 variables is written as a product of smaller conditional distributions. The joint distribution is the complete probabilistic description of the system. In principle, it assigns a probability to every possible combination of values for A through E. The graph shows the same dependency structure. Each circle is a random variable, and each arrow shows a direct probabilistic dependency between random variables. For example, the arrow from A to B matches the term B given A. The arrows into E matches E given B and C. Notice what an absent edge can tell us as well. Once the parents of a variable are known, the Bayesian network model allows us to treat that variable as conditionally independent of its other non-descendants. This is the local Markov property, and is the reason why large joint distributions can be replaced by smaller local distributions. PGMs are used in many areas such as medical diagnosis, computer vision, language, robotics, and decision systems. Judea Pearl helped establish many of the key findings behind this field and received the 2011 ACM Turing Award for work that includes probabilistic graphical modeling and causal reasoning. Now let us make the discussion concrete with a simple example. Suppose we want to predict the price of a house from properties or features about that house. We begin with a linear model. Here, y is the value that we want to predict. The vector x contains the input features, and the vector beta contains the weights learned by the model. Their inner product produces a single predicted value. In this example, y is the house price. The equation is a model of the relationship between house price and features. To keep this example simple, we're only going to be considering one feature, which is the house size. A real model could use many more features such as the number of rooms, the area, the location, or the age of the building. Each point on this plot is one observed house. Its horizontal position corresponds to its size, and its vertical position corresponds to its price. The dashed line is the pattern found by the model. Since larger houses tend to cost more, the fitted relationship slopes upward. The compact vector equation can now be expanded into a weighted sum, where each feature xi is multiplied by a weight beta I, and those contributions are added to form the prediction. You should have noticed that our model does not perfectly predict house price. The points do not lie exactly on the line, and that's because the real world is of course not perfectly predictable, so a point estimate is only part of the answer. So why can two houses with similar features sell for different prices? Our model cannot record every detail. Buyers and sellers may value the same house differently. The condition of the house, the timing of the sale, or an urgent offer may also change the results. Even at this one input value, with the same features, several prices are plausible. So we do not only want one predicted price, we want a conditional distribution over possible prices. The expression P y given x describes how plausible each output y is after the observed features x have been fixed. A probabilistic model describes variables with probability distributions. The goal is to specify a coherent joint model from which many conditional questions can be answered. On the left are observed feature and price pairs as we had before. In the general problem, x may be a vector with many features. In this example, x stands for one simplified feature such as the number of rooms. We use the observed data to build a model. Specifically, the expression px, y is the joint distribution of the inputs and the output. It describes their uncertainty together. The small Bayesian network says that y is conditioned on x. Once we have a joint model, we can then ask questions in either direction. For example, if a house price is 100,000, what is the probability that the house has 3 rooms? That query is written as follows. With PGMs, the answer is not forced to be yes or no, and it is rather represented as a probability. We can also hold the feature value fixed and look at our belief over y. The green curve shows which prices the model considers more or less plausible at that input. Here, a belief is simply a probability distribution that represents our current knowledge after the evidence has been included. It provides a prediction together with a degree of certainty. In graphical model algorithms, the word belief often refers to a marginal or conditional distribution computed for one variable or one cluster of variables. Reasoning under uncertainty leads to 3 practical questions. First, there's a trade-off between a simple model and a rich model. A richer graph can represent more dependencies, but it may need more data, more parameters, and more computation. A simple graph, however, is easier to use, but it may miss an important relationship. Second, we must select a model that fits the problem and our limits. The amount of data, the quality of that data, and the available computing budget all affect this choice. The most detailed model is not always the best model for the evidence we have. Third, we have to update what we believe. We begin with a prior belief about y, and we observe evidence x, and combine the two to give the updated distribution p of y given x. These 3 ideas, trade-offs, model selection, and updating, will return throughout the tutorial. Let's run through a quick example. Consider a spam filter. The class variable c tells us whether an email is spam, and the variables w1 through wn record words or word features in the message. For accurate spam classification, we can express a very detailed joint distribution as we see here, which includes correlations between pairs of or larger groups of words. For example, credit and card together may carry information that neither word carries alone. Our prediction task is to compute the probability of the class after observing all of the words, which is written as follows. For a binary classifier, this posterior gives 1 probability for spam and 1 for non-spam. The box now samples 1 local word pattern. For this pattern, the spam probability is 0.31. Think of this as one slice through a very large table of possible word configurations. Similarly, for all other word combinations, the spam probability changes. With language and spam classification, these changing probabilities show why interactions between words can be useful. The meaning of one feature or word may depend on which other features are present in the message as well. Such a rich joint distribution has a cost, however. As the number of word variables grows, the number of parameters grow very quickly as well. For this unrestricted binary model, there are n plus 1 binary variables, the class and n word indicators. They have 2 to the n plus 1 possible joint configurations. That is exponential growth, as we can see here. Adding only 1 more binary variable doubles the number of table entries. Even a moderate vocabulary makes the full model impractical to store, estimate, or query reliably. This is one form of the curse of dimensionality. So in reality, we need a structural assumption that can keep the useful part of the model while making learning and inference manageable. That assumption is conditional independence. 2 variables are conditionally independent given a third when learning one of them provides no additional information about the other once a third is known. If we keep the class and the word variables and simplify the relationships among those words, We could imagine that the observed words are click here to win money. Some word pairs often occur together, and some may nearly be unrelated in an ordinary email. Naive Bayes makes a strong, useful assumption. Once we know the class, the word features are independent of one another. The class is the shared parent that explains their connection, so words may still be statistically associated before the class is known. It is their remaining dependence within each class that the model ignores. This is called naive because real words are not perfectly independent. Phrases and syntax clearly create residual correlations, yet the approximation can still classify well because the model does not need to reproduce every detail of language in order to separate two classes effectively. The graph now gives a much smaller factorization as seen on the right. The left side of this equation is the joint distribution over the class and every word feature, and this is equal to the prior probability of the class before reading the words, and that is multiplied by the product of the likelihood of each observed word conditioned on the class. Now if we compare the size of this model with the unrestricted one, we can see that the parameter count is now 2n plus 1, which grows linearly with the number of word features. The independence assumption has therefore turned an exponential problem into a far more tractable one. We have exchanged expressive power for lower sample and computational requirements. The rest of the tutorial is organized around 3 tasks: representation, inference, and learning. It is helpful to keep them conceptually separate, even though a complete application usually needs all 3. Representation asks how we encode a probability model as a graph. We must choose the variables, the edges, and the local numerical objects. That is, the conditional probability distributions in a Bayesian network, or factors and potentials in an undirected model. The resulting graph should make the important dependencies and independence assumptions visible. Inference asks a question using a model that we have already set up. The inference process produces posterior probabilities, marginals, most probable explanations, or other quantities of interest. The graph structure can make these calculations much cheaper than enumerating the entire joint distribution. Lastly, learning asks how we can fit the model from the data. If a graph is fixed, we may estimate only its numerical parameters. If the dependencies are unknown, we may also learn the graph structure. With hidden variables, learning can require repeatedly alternating between inference about the hidden states and parameter updates. These tasks depend on one another. A representation determines which inference algorithms are available, while inference is often used inside learning, and the amount of data may determine which representations can be learned reliably. We will now briefly go over each one of these tasks. Let's begin with representation. The Bayesian network is a directed acyclic graph. Its arrows describe how each variable is conditioned on its parents. One alternative representation is a Markov network. On the right, we will convert the same structure into an undirected graph used in constructing a Markov network. This process is called moralization. It has 2 steps. First, connect every pair of coparents, and then remove the arrowheads. So node E has parents B and D, so we connect those coparents with an undirected edge. And node F has parents C and E, so we connect C and E as well. We do this for each child that has more than one parent. After the coparents are connected, we remove every arrow direction. The result is an undirected Markov network. The conversion preserves the connections required to express the Bayesian network factors in an undirected form. The left graph keeps the original directed story, while the right graph shows the moralized structure used by later algorithms. More broadly, representation includes choosing the variables, choosing a directed or undirected graph, and specifying the local probability tables or factors attached to that structure. Inference means computing probabilities from a model after some variables may have been observed. Some model structures allow efficient exact inference. Larger or more densely connected models may approximate inference. Here, we will look at exact sum product message passing and keep every calculation symbolic, just as an example. The graph on the right is a junction tree, which is also called a clique tree. It is obtained by organizing clusters of variables into a tree. Each ellipse here is called a cluster, while the small box between two clusters is a separator set, or subset, containing the variables shared by those neighboring clusters. A valid junction tree satisfies the running intersection property. If a variable appears in two clusters, it must also appear in every cluster along the unique path between them. This ensures that information about the variable remains consistent as messages travel through the tree. The local factor at cluster I is written as psi of I. It represents the product of the original model factors assigned to that cluster, including any observed evidence. A message is written with the Greek letter mu. A cluster belief is written, therefore, as B of I. Every sum product message follows the same pattern. Multiply the sender's local factor by all messages arriving from neighbors other than the destination, and then sum out every sender variable that's not in the subset. The result can only be a function of the shared subset variables. Don't worry if this equation seems complicated right now. We'll be sure to go over it in detail later on in the video series. This tree has 3 leaf clusters around the central cluster. Because it is a tree, there is exactly one path between any two clusters. We'll first pass messages inward, form the central belief, then pass messages outward and form the 3 leaf beliefs. This 2-pass schedule is enough to distribute information from every cluster to every other cluster in a junction tree. First, cluster C1 sends a message to cluster C0. Its variables are A, B, and D, and the separator set is B and D. So variable A is private to the sending side of this edge, so we marginalize it by summing over all of its possible values. The message that crosses the edge is therefore a function of only B and D. Next, C2 sends the message 2 to 0. Cluster C2 contains exactly B, C, and E, which are also the separator variables. No variable needs to be summed out in this example. The outgoing message is simply the local factor, psi2. Then C3 sends message 3 to 0. Its separator is C and E, and variable f is not shared with the central cluster, so we sum f out and retain only a function of C and E. The central cluster has now received information from all 3 branches. Its belief, B0, is proportional to its local factor, psi0, times those 3 incoming messages. Each message summarizes all factors on its side of the corresponding edge, so this product incorporates information from the entire tree. The proportionality sign reminds us that the expression may be unnormalized. Dividing by the sum over all assignments of B, C, D, and E, we turn it into a valid probability distribution whose entries sum to 1. Now the outward pass begins. To send a message from C0 to C1, we combine psi0 with the messages that arrive from clusters 2 and 3. We exclude the message from C1 and sum out C and E, leaving a function of B and D. For the message to cluster 2, we use the incoming messages from clusters 1 and 3, but exclude the message from 2 to 0. Of the central variables B, C, D, and E, only D is absent from the destination subset. We sum out D, leaving a message defined over B, C, and E. For the message to cluster 3, we use the incoming messages from C1 and C2. We sum out B and D because neither appears in subset O3. The result is defined over the shared variables C and E. Cluster 1 can now form its belief by multiplying psi1 by the message from cluster 0. The local factor supplies information from the cluster belief itself. The message summarizes the rest of the tree. Cluster C2 does the same with psi2 and the message from 0 to 2. And finally, the third cluster combines psi3 with a message coming from 0 to 3. As with the central belief, each of these leaf cluster beliefs can be normalized after multiplication. Since this is a junction tree, calibration only required 2 passes. Once both passes are complete, every cluster has the information needed for its calibrated belief. Calibration means that neighboring cluster beliefs agree on their shared subset after marginalization. We can then obtain a single variable marginal from any cluster containing that variable. Our third task is learning. So that's fitting a model to real data. Representation tells us the form of the model, and learning determines the unknown numerical values and sometimes the structure itself using observations. The parameter theta controls the process that generates hidden states zi and observed samples xi. Depending on the model, theta could be a mean, a variance, a regression weight, or an entire conditional probability table. The hidden variables zi represent relevant quantities that are not directly observed, such as an unrecorded category or latent state. The arrows describe the forward generative direction where parameters influence latent states, which in turn influence observations. Learning works in the opposite direction. Given a dataset, we use the observed samples to estimate theta, or to form a probability distribution over its possible values. If the zi variables are unknown, inference about those hidden states may become part of the learning algorithm. Computational learning theory asks what can be learned from a limited sample and with feasible computation. In particular, it studies whether performance measured on training data will carry over to fresh examples from the same population. This is the problem of generalization. Bayesian statistics give another view of learning. Instead of treating theta as an unknown fixed number to be replaced by a point estimate, we use a distribution to represent uncertainty about its value. Let's do a conceptual example. If we begin with a bell-shaped Gaussian prior centered near 0, the prior may encode earlier measurements, domain knowledge, or a preference for smaller parameter values. After a first few observations, the likelihood favors positive values of theta, so the posterior moves in that direction. It does not jump to a single estimate. It remains a distribution because 2 samples leave substantial uncertainty. After a few more observations, the posterior now balances both kinds of evidence. Parameter values that explain the full sample receive more probability, while poorly supported values receive less. The posterior is far more informed than the prior and begins to concentrate. After all observations, the posterior is narrower and shifted towards parameter values that better explain the pattern. The prior still contributes, but as consistent evidence accumulates, the likelihood usually has an increasing influence. Once we have the posterior, we can summarize it with a posterior mean or a maximum a posteriori estimate. More importantly, we can propagate the entire parameter uncertainty into a posterior predictive distribution for a future observation. So computational learning theory asks how well a learned rule will generalize and how that guarantee depends on sample size and model complexity, while Bayesian statistics show how prior knowledge and observed evidence combine into an updated distribution over unknown quantities. They answer different questions, but both make uncertainty about learning explicit rather than hiding it behind a single fitted number. This completes our first overview of representation, inference, and learning.